Hi everybody, welcome to the start of our discussion of the planets in detail. This video will be about Mercury, our innermost planet, and in many ways the most extreme planet in our solar system. Here's a true color image of Mercury taken by the Messenger spacecraft during its recent visit and orbit around the planet. So, some quick facts about Mercury. Its rotational period, about 59 days, and the time it takes to go around the Sun is about 88 days. It turns out that its solar year is exactly 1.5 times its rotational period. It's what we call a 3-to-2 orbital rotational resonance. It rotates exactly 3 times for every 2 times it goes around the Sun. Orbital eccentricity, 0.2. That's actually the highest for any planet in the solar system. In other words, Mercury has the most non-circular orbit among all of the planets in the solar system. And it attained that feat, so to speak, or it went into first place when Pluto was demoted officially back in 2006. Pluto's orbit is a little bit more eccentric than Mercury's. Mass of Mercury, it's a little bit over 1/20th of Earth's mass. Its radius is a little bit over 1/3 of Earth's radius, and it's bigger than our moon, a good bit bigger than our moon. Now, on average, it's about 0.4 AUs from the Sun. Again, I kind of recommend knowing the relative distances of the planets from the Sun. So Mercury about 0.4 AUs, Venus 0.7, Earth is 1, Mars is 2, Jupiter is 5, Saturn's 10, Uranus is 20, and Neptune's about 30. And again, all those values are rounded, but just rounding them like that makes them, I think, a bit easier to understand, or at least easier to remember. And from there, you can get a mental picture of what our solar system kind of looks like. Here's what I mean about Mercury being the most extreme planet, though. The temperature range. It goes as low as 80 kelvins. That's actually colder than the coldest temperatures on Mars, but all the way up to 700 kelvins. That happens because of the fact that Mercury has basically no atmosphere. It has what we call a surface-bounded exosphere. And it has a very long rotational period. So the nighttime side can get very, very cold, because it just radiates off into space, and it's a long time before that nighttime side turns back into the daytime side. What that also means is that it's always very cold in craters near the poles, and that's going to have some interesting implications that we're going to get to later. Other facts. Surface gravity, about 3.7 meters per square second. Interestingly, it's about the same as Mars, even though Mars is a lot more massive. Mars is also a bit less dense than Mercury, so at the surface, the gravitational pull is about the same. Axial tilt of Mercury, basically 0 degrees. That's 2 arc minutes, so 1/30th of a degree. So again, that means that any craters that are near the poles are never, ever going to see sunlight. It has no rings or moons, and it also has quite a dark surface, similar to the darkness of our moon. Our moon's albedo ranges from about 0.06 to 0.10. So Mercury has quite a dark surface. Now, albedo, remember, is the surface reflectivity, the percentage of incoming sunlight that gets reflected. A perfectly reflecting body would have an albedo of 1. Now, the atmosphere. We mentioned that Mercury has basically no atmosphere. It ranges from about 1 femtobar to about 1 picobar, where Earth's atmosphere is about 1 bar. A bar is defined to be 100,000 pascals exactly. Earth's atmospheres are more than that, but femto, you might recall, is 10 to the minus 15, and pico is 10 to the minus 12. So we're talking about an atmospheric pressure that's somewhere between a quadrillionth and a trillionth of Earth's atmospheric pressure. So it's a very, very thin atmosphere. And it's not really a real atmosphere. It's what we call a surface-bounded exosphere. On Earth, our atmosphere has pressure because of collisions between particles and each other, kind of rebounding off of each other and then rebounding against anything that's used to measure pressure. Whereas in the case of Mercury, the atmosphere is so thin that the gas particles hardly ever collide with each other. They basically go on parabolic types of trajectories. And that's the characteristic of something called an exosphere, where you get into an atmosphere where it's so diffuse that your particles are generally on parabolic trajectories. Well, Mercury has no real atmosphere where the particles really collide with each other. The only thing it has is particles that have these trajectories that are essentially like balls being tossed up in the air and they come back down. What composes this weirdly very thin atmosphere? Well, it's about 42% molecular oxygen and also 29% sodium. That's a strange thing to have in an atmosphere, but remember, Mercury is the closest planet to the Sun. So during the daytime side, you're going to have some sublimation and interactions with the solar wind and stuff like that. And then a little bit of hydrogen and helium. Those are going to be coming from the Sun, and then trace amounts of other stuff after potassium. Other facts. Because of the fact that Mercury has that weird orbital to rotational resonance, that actually means that the time between from sunrise to sunrise, or I guess high noon to high noon, on average is about 176 Earth days. In other words, 2 Mercury rotation periods. So we'll get to that on a slide soon. A little bit of trivia. Craters on Mercury are named after artists, painters, musicians, etc. Now, Mercury's orbital eccentricity led to a very good test of general relativity back in the 19-teens, because this was something that resulted in this weird orbital precession that was not able to be accounted for. Now, in truth, all of the planets have some sort of observable precession of the axes. In other words, the perihelion, which is the closest distance to the Sun for a planet, it changes its location with respect to the background stars over time. Most of the time, that's because of the effects of the other planets, like Jupiter, Saturn, other planets, etc. In the case of Mercury, Mercury has an overall precession that's a lot larger than this 43 arcseconds per century. I've forgotten exactly what it is. But 43 arcseconds per century is unable to be accounted for by considering the effects of Jupiter and the other planets. And this was unexplained. For a long time, scientists thought that there was this planet in between Mercury and the Sun called Vulcan that caused Mercury to get disturbed in its orbit. But it turns out, no, it's actually because of the fact that Mercury has this eccentric orbit and it's close to the Sun, and Newton's law of universal gravitation is not exactly correct. And Einstein's general relativity was able to explain that discrepancy. So that was a big victory for general relativity. The density of Mercury. Mercury is the second densest planet in the solar system. In fact, it would be densest if it wasn't for the fact that it has a much smaller gravitational field than Earth. Earth's gravity is large enough that it's able to compress the materials more than on Mercury, but if they had the same gravitational field, Mercury would actually be denser. In other words, it's composed of denser materials. It's just smaller gravity means there's less compactification. Also, Mercury has an incredible core. Its core is very, very big, and we really do not know 100% why that's the case. The old theory was that a giant impactor early in our solar system's history stripped away a lot of Mercury's previous crust, so we got rid of that, so now you're just left with the denser materials. But this is starting to have some trouble based on some recent data from the Messenger spacecraft. So a new theory is that the temperatures that Mercury experienced soon after its formation were high enough that the early crust was vaporized, and that left behind the denser material, so kind of going back in with our understanding of how the planets formed to begin with. So hopefully we'll have a better idea of this when the next spacecraft arrives into Mercury orbit in 2025, that being the Bepi-Colombo spacecraft. Here is an artist's cutaway of the interior of Mercury with some nice little jazzed up artistry here, but it has a solid inner core, and outside of that it has a somewhat molten outer core. I should say really semi-molten. Parts of it are molten, we think, parts of it not so much, parts of it are somewhat solidified, and that has weird implications for Mercury's magnetic field that we're going to discuss later. And then it has this division between the mantle the mantle and the outer core, known as the anticrust, and that seems to help to prevent some of the cooling that you would normally expect for a planet of Mercury's size. Now, speaking of cooling, why do planets like Earth, for example, have a molten outer core, a liquid outer core? How is it hot enough to get a liquid outer core? So, the common misconception that you will sometimes hear from middle school or elementary school textbooks is that this is due to compressional heating from the layers above. That is not true. That actually accounts for a relatively small percentage of it. The actual reason that it's so hot in Earth's interior is because of the heat generated from the decay of radioactive isotopes, in particular uranium-238, thorium-232, and potassium-40, all of which are relatively common radioactive isotopes. If you have a large rocky planet, it's going to have a lot of these isotopes infused within, and as they decay, the heat is going to so the idea is that you get a parent nucleus, it decays into a daughter nucleus. You might think, okay, why does that generate heat? Well, remember, it emits radioactive particles, and these radioactive particles end up themselves having some kinetic energy, which they transfer to the region around. But the big generation of it has to do with the fact that the daughter nucleus is usually in what we call an excited state when it gets decayed to from the parent nucleus. So you've heard this term about excited states when we talked about atoms back in a previous unit, how an atom will have an electron in an excited state, and when that electron goes to a lower energy level, it emits a photon. In the case of atoms, those photons are usually in the visible part of the spectrum or the infrared part of the spectrum, sometimes ultraviolet part of the spectrum. But in the case of atomic nuclei, we're talking about much larger changes in energy, and these energy differences correspond to photons of gamma rays. Gamma rays are very energetic, and as these gamma rays are emitted, they bounce off of all kinds of other particles around them and impart them with a lot of energy. And as they do so, and remember, what is temperature? It's average kinetic energy. These things get heated up, and they get hot enough that you're able to melt things. So if you have a large planet, a lot of that, this happens, this emission of gamma rays goes off randomly in all directions. But what that means is that on average, you're going to have more of them coming toward the center than out toward the edges, because toward the edges, they're more likely to escape out. Once they escape out, they're not going to be bouncing around anymore. But when they're closer to the center, they're more likely to be bouncing around just randomly. So you're going to get more central heating that way. Also, the edges are where you get radiation. In other words, you radiate from the edge of the planet. So that radiation is a loss of energy. So it takes a while for that heat to get from the center to the edge. And also it's being resupplied by the decay of radioactive isotopes. In the case of a large planet like Earth, you expect this to happen for quite a long time. In the case of Earth, it's going to keep happening for about the next few billion years. And it's been happening ever since Earth formed. Of course, it was greater in extent soon after Earth's formation. But in the case of something like Mercury, you don't expect it to last as long. In fact, you would normally expect Mercury to be frozen out by now. In fact, you would also kind of expect Mars to be frozen out by now. And indeed, Mars is frozen out by now. So that's something that we're going to discuss when we talk about Mars later on. In any case, though, due to this internal heating, you get this molten outer core. The inner core is solid. Try to think to yourself why the inner core is solid. The inner core is solid because of the pressure of the liquid outer core. So that does create pressure, and under increasing pressure, you get solidification. But in any case, when you have this molten inner core, just kind of going back to this slide, that ends up convecting. I mean, things naturally want to convect when you have some sort of temperature difference between the internal part and the external part. There's going to be an exchange of energy. If it's a completely solid body, that exchange of energy is going to happen by either conduction or radiation. Radiation mainly happening from the surface, but it also happens on the internal parts as well. In other words, you have a higher energy photon getting exchanged and bumping into things and becoming a lower energy photon on the way out. That's radiation. Although I guess you could make an argument that there's conduction associated with that as well. But really, conduction is where you have surfaces touching or atoms touching, and they exchange energy with each other, with higher energy atoms losing energy to lower energy atoms. But convection occurs when you're dealing with a liquid or a gas, and that's when you have bubbles of higher energy forming, and those bubbles have higher temperature and are less dense, so they end up rising to the top. And as they rise, they expand and impart the energy to the outer layers. That's something that we'll talk about in more detail when we talk about stars and our sun. but it happens on the interiors of planets, especially when you're dealing with liquid interiors. And this convection, as this happens, helps to generate a magnetic field, because this, liquid, you're talking about liquid iron here, and you're dealing with a lot of free electrons here that are moving, and moving charged particles generate magnetic fields. So when you combine that with the planet's rotation and the convection, you end up generating a magnetic field. In the case of Earth, it's a sustained magnetic field. It's a self-sustaining process, such that you can imagine Earth is like kind of a giant bar magnet. In the case of Mercury, strangely enough, it seems that Mercury is kind of like a giant bar magnet as well. And that implies that Mercury does have at least a part inside that is still molten. And it's strong, the field is strong enough, about 1% of Earth's magnetic field strength, that you do expect that it's molten. Now, if you look carefully at this graph, see this part with the hash mark right here is supposed to coincide with the center of Mercury. But notice where the peak of Mercury's magnetic field is. The peak of Mercury's magnetic field is not at the center. Instead, it's as if Mercury, instead of being modeled by a giant bar magnet in the center generating the magnetic field, it's like the giant bar magnet is displaced somewhat off-center. Now, we're still not completely sure exactly why Mercury's core hasn't completely frozen, but we now believe that there may be enough sulfur infused in that core, that the sulfur combined with the molten iron, sulfur is also molten at those temperatures, sulfur actually has a relatively low melting point, can act as an antifreeze and keep the core liquid for longer than what you would otherwise believe. But it's kind of in the process of starting to freeze out, perhaps, because that magnetic field is not centered on the core. It's displaced about 16% toward the north geographic pole. Volcanism used to exist on Mercury, maybe even as recently as 1 billion years ago or less. But currently, Mercury is believed to be geologically dormant. Now, these pictures on this slide and this next slide, these are not pictures of volcanic caldera. These are pictures of impact craters. So why am I showing them talking about volcanoes? Because, as you can see, they are smooth on the interior. They are smooth on their interiors because of recent magma flow. Recent lava flow there. Recent magma rising to the surface and flowing as lava. So, something to keep in mind. These smooth areas, you're dealing with volcanic lava flow in the reasonably recent past. Now, another interesting thing that Mercury has in its geology is something called scarps. Scarps are actually on a number of the planets. They're on Earth, they're on Mars, but they're most prominent on Mercury. And the reason is that Mercury has something that's happening that's different than any of the other planets right now. Mercury is in the process of freezing on the interior. And by freezing, we're talking about the molten iron solidifying. Now, what do most substances do when they solidify? They compress. Water is the main exception to this. Water is at least the most well-known exception to this, in that water expands as it freezes, which is good because that causes ice to float on the tops of lakes instead of sinking, causing the whole lake to freeze, and therefore life would end up ending in lakes every time winter came. But so luckily water expands when it freezes. But most substances contract when they freeze. And so as Mercury's interior freezes into solid iron and contracts, well, that causes buckling to occur because outer layers kind of collapse in on those, but the surface is already frozen. The surface froze long ago. So it can't simply contract as it freezes because it already froze. It's already done that. So instead, the surface has to buckle to accommodate the fact that you would otherwise have gaps in the interior as this freezing process continues. So here's a nice long scarp going through some impact craters. So yeah, again, when Mercury formed, all of its core was molten, but as it continued contracting, you got more and more of these scarps, and those continue to form today. Another big feature of Mercury, and literally a big feature of Mercury, is the Caloris Basin. It's a giant impact crater. Depending how whether you want to call certain other things impact craters, the Caloris Basin may be the largest impact crater in the solar system. It's close to 1,000 miles wide. So here's a picture of the whole thing. And the last picture, you kind of see it along over here. It's a very old impact basin. It probably formed either during the late heavy bombardment or maybe even before that. But yeah, lots of craters have formed on top of it since then. And the impact itself was energetic enough that it created shock waves going all around the planet. And when those shock waves were created, they would eventually meet at the opposite side of the planet at about the same time. The opposite side is known as the antipode, the wife of Uncle Pode. No, whenever you talk about a point on a planet, the point that is directly opposite to it on the other side of the planet is known as the antipode. And when these seismic waves met at the antipode, they resulted in kind of temporary liquefaction of the surface there and a creation of mountain building, all in one quick event. And this was the creation of the so-called weird terrain, which is exactly at the antipode of Mercury, or often called jumbled terrain. And this was literally created by seismic waves upending the surface on the opposite side and creating mountains. And some of these are fairly high. I mean, we're talking about 10,000 feet or so in some cases. And then there are other cool features as well, ones that you don't need to know about so much. You need to know about the Caloris Basin, and you need to know about why it has the jumbled terrain on the opposite side. But other than that, no, you don't need to know about this, but it does look cool. Now, orbital characteristics. As a result of the combination of Mercury's very slow rotation and the fact that it has this resonant, highly elliptical orbit, what that means is that since the orbit is very elliptical and the rotation is very slow, there are times when Mercury is far away from the Sun when Mercury is rotating a little bit faster than its revolution around the Sun. What I mean by that is the angle between Mercury and Sun, between Sun and Mercury, increases by a slower rate than the angle between Mercury's center and a point on the surface would increase as Mercury rotates. That's usually the case, because on average Mercury rotates once every 58 days, and it goes around the Sun every 88 days. But when Mercury is closer to the Sun, there are some points where it's actually orbiting around the Sun faster. In other words, the angle between Sun and Mercury changes at a greater rate than does the angle from the center of Mercury to an edge on the planet. And the result of that is that the Sun seems to go backward when that happens. But we're going to get to that. First of all, the 3-to-2 orbital resonance. So as we mentioned before, Mercury rotates exactly 3 times for every 2 times it orbits the Sun. Now, because of the fact that Mercury is so close to the Sun, this resulted in tidal deformation. Mercury got stretched, but also because of the fact that it has an elliptical orbit, it couldn't be a 1-to-1 resonance like our moon is around Earth, where you always have the same face of our moon showing toward the same face of Earth pretty much. So in the case of Mercury, it became a 3-to-2 orbital resonance. So, but that whole tidal stretching and everything did cause Mercury's rotation to slow down a lot, so that when consider a point showing toward the Sun initially, well, after Mercury has undergone half an orbit, that point has only gone around 3/4 of a time. And then once it gets back to where it is, that point has gone around 1.5 times. But notice that point has not yet seen the Sun again. By the time it's gone around once, that point is at midnight. So like going from here, then to here, it's like, okay, now we're talking about, say, like mid-morning or something like, well, I actually take it back. We're starting at noon. So now we're talking about mid-afternoon. And then after half an orbit, you're in evening, you're at sunset. And then continue on in the orbit, you have to get back to where you started before you get to midnight. And now the cycle begins again, except you're at midnight, starting back, and then after another complete orbit, you're finally back to high noon again. So a solar day on Mercury is actually 2 rotational periods. So that's kind of cool in that regard. Now, in any case, as I was also mentioning, when Mercury is near perihelion, it's actually revolving around the Sun faster than it's rotating. So the result is that the sun seems to rise in the west and set in the east at that point. But that doesn't last long. Eventually, Mercury gets farther away from the sun, and a result of that is that the sun kind of resumes its normal track going from east to west. Well, what that means is that depending where you are, you can see a double sunrise or a double sunset, or the sun will be going across the sky, then it slows down, and then it reverses direction, and then slows down again, and then resumes its normal track. And this occurs every solar day on Mercury. So there's a nice video showing how this appears, and I'll try to remember to link to this video in the YouTube notes. So another diagram showing the rotation. Now, radar observations on Mercury. In the 1990s, the Arecibo radio telescope was used to make a careful map, at least as careful as could be obtained from Earth using a big radio telescope, of the surface of Mercury. And what we're talking about is we're mapping the craters, mountain features, and stuff like that. Surprise, surprise, when the radar investigated the craters near the North and South Poles, it was found that there were no return signatures. Well, when you have no return signatures, that means you're talking about a smooth region there. Perfectly smooth. But it's perfectly smooth inside of a known crater. So the realization was that there was probably water ice. Maybe something else, like some sort of sulfur compound or sulfur itself that could be solid there as well and smooth after having come in as a liquid. But the thing is, water is much more common than sulfur. Water is one of the most common compounds in the universe. So this is a picture of the Arecibo Observatory before it collapsed in late 2020, because things like that happened in 2020. So taking negatives of these images, the realization is that these smooth areas, which don't return the radar signatures, are all inside of these craters. So, what's going on there? Well, it turns out it actually is water ice, because the Messenger spacecraft was able to fly directly over these craters and observe that, yeah, it is completely dark there, so you can have water ice, and it registered the signatures that you get from colliding neutrons, which collide in a certain way with water ice and in different ways with other substances. So from that, we basically confirm that, yes, there is water ice in the polar craters on Mercury, which is really neat. Now, in terms of the amount of water ice there, it turns out it's estimated to be great enough that it would encase all of District of Columbia in a block 2.5 miles deep. Now, of course, one can make jokes about how the fact that nothing would really change in this country because Congress doesn't really do much there anyway. But still. So, it's a lot of ice. A lot of ice on the closest planet to the sun. Of course, you don't get that at the equatorial latitudes because when Mercury rotates, the sunlight will get to the bottom of those craters and it will sublimate everything there, turning it from solid to gas, unless it has a melting or boiling point that is a good bit higher than the temperatures that you get there. Now, about the atmosphere. We've already mentioned about hydrogen and helium coming from the solar wind, but there's also this potassium and sodium and magnesium in the atmosphere, and we're not completely 100% sure where that comes from. It could come from micrometeorite impacts, but hopefully the Bepi-Colombo spacecraft, when it arrives in 2025, will give us more insight on that. Now, also, Scarps on Mercury are very extensive, we now realize, based on the results from the Messenger spacecraft, and they're more recent than the impact craters, so in other words, they formed more recently than that. And also, volcanic activity has certainly extended into less than 2 billion years ago, and maybe as recent as less than 1 billion years ago. So just showing some pictures from the Messenger spacecraft. This is somewhat enhanced color to bring out certain features and to show where certain types of compounds exist on the surface. So more enhanced color. And this is slightly enhanced color, showing some more recent impact crater compared with the others. You can tell that certain impact craters are more recent because they have more sharply defined ridges. Meteorite impacts and micrometeorite impacts over time gradually wear away crater ridges even on a planet or moon that has no atmosphere. So from that, you can estimate the ages of craters. Now, sulfur. Here's the weird thing about sulfur. It melts at 388 kelvins and vaporizes at 718 kelvins. Well, Mercury's highest temperatures are a little bit less than that, but when water gets to 200 degrees Fahrenheit, with the boiling point being 212, it still is going to evaporate rather quickly. So you would expect that the sulfur shouldn't really be in much abundance on Mercury's surface. So the fact that it is there kind of makes us wonder. In fact, the general idea is that it must be coming from underneath the surface, meaning that Mercury has more sulfur than one might otherwise believe, which would actually explain the fact that Mercury's core has still not solidified completely, because remember, as we mentioned, sulfur mixed with iron acts as an antifreeze. This is further supported by the discovery of these hollows, the deathly hollows, not deathly hallows, but the deathly hollows on Mercury's surface that look like this. These are not volcanic vents. These are not impact craters. Instead, what seems to be happening here is that some sort of volatile substance under the surface is sublimating. It gets heated up, it sublimates, and as it does so, it escapes out and causing a vacuous region on the inside of which the overlying surface collapses, creating these hollows. So this could be created by volatile sulfur and or other volatile compounds and elements like sodium or magnesium and stuff like that. Okay, so anyway, a lot of our current knowledge of Mercury has come from the Messenger spacecraft. Messenger actually crashed into Mercury, intentionally, I might add, on April 30th of 2015. But as it did so, as it was getting closer and closer to the surface, it took some very close-up pictures. Now, this is the closest picture that we have. The image itself is 1 kilometer across, and each pixel shows details as small as about 2.1 meters across. So we're talking about small impact craters here, impact craters that are meters wide. Now, you might notice that this picture is quite grainy. Why is it grainy? Is it because of all the sand and dust on the surface of Mercury? No, it's grainy because, think about it, when the spacecraft, it's in orbit around Mercury, but it's this close to the surface of Mercury, so the features on the surface are going by at a really high rate of speed. So in order to be able to photograph them, you have to use a very, very high ISO type of feature on the camera. But as you photographers know, when you increase the ISO to very high numbers, you get more graininess in the picture. Some remaining questions. So we've gotten a lot of information about Mercury from the Messenger spacecraft, but what more remains to be answered? So first of all, we'd like to know more about Mercury's atmosphere, and also how does Mercury have things like sulfur on its surface that should be pretty much evaporated by now, unless it's coming from a source underneath, and why is Mercury's core so large? How exactly did Mercury form? That question probably goes a long way toward understanding why Mercury's core is so big. And what exactly creates the hollows? Is it sublimation of sulfur? Is it sublimation of something else? We're still trying to figure that out. And does Mercury's magnetic field change with time and location? In other words, will it have a slightly different value and positioning when Bepi-Colombo arrives in 2025? So, Bepi-Colombo is on its way. It was launched in October of 2018. It'll actually consist of 2 different orbiters that have different instruments that will allow us to simultaneously monitor certain things about Mercury from different perspectives. Here's an artist's conception of Bepi-Colombo. Summary of some important points. As you know, Mercury is the smallest and least massive of the planets in our solar system. It has no moons, no rings. In fact, none of the interior planets have any rings at all. But Mercury also has no moons. It has this 3-to-2 orbital resonance with the Sun. And when you combine its slow rotation with Mercury's very elliptical orbit, such that it's far from the Sun at some points and therefore not moving very fast, and close to the Sun at other points and therefore moving a lot faster, you can get double sunrises or double sunsets depending on where you're seeing it on the planet. Mercury has almost no atmosphere. and therefore, combined with its very slow rotation, has the most violent temperature swings of any planet in the solar system from day to night and back. The Messenger spacecraft give us most of our current understanding of Mercury, but we still lack things that we hope will be answered by the Bepi-Colombo spacecraft. Mercury has, on average, the densest material of any planet of the solar system, even though Earth is actually denser when you take Earth's mass and divide by its volume. That's because Earth has larger gravity. But in terms of the substances, the materials themselves on Mercury are denser. Basically, Mercury has lost, we think, a lot of its original crust. And crust is the least dense. That's why it's on the outside. It floated to the top when the planet formed. Mercury retains some relatively large impact craters. Remember the Caloris Basin, 1,000 miles wide, from collisions in the distant past. And the small magnetic field probably indicates that Mercury's core has not yet completely frozen. But as it continues to freeze, you get contraction, and the outer layers on that, above that contract, and then eventually the surface has to contract and buckle, creating scarps. So here is a final nice picture of Mercury taken by the Messenger spacecraft. So if you have any questions or comments, please leave them in the comment section on YouTube. And I hope to see you all next time for the video on Venus. Have a good one.